We can start. So, good morning. I hope you slept well and enjoyed the barbecue yesterday. Today we have more technical sessions. So it's more on post-Shannon theory. So for the people working more on molecular communication, please ask if something is not clear. So today we will really have only talks on post-Shannon theory, and people want to explain it. And of course, the idea is to apply it also in molecular communication purpose. There's a way to apply it there, and therefore it would be nice if you understand this. And so therefore, be open and ask questions. Also, you can interrupt people here. I think it's possible. We are not so many people, and we don't have to be so strict in time.
I actually prefer it if you like during the talk you just raise your hand and ask. So
yeah, so the first talk will be presented by Pau. You know him already from yesterday from the poster. He already spoiled his talk a little bit, since he was so kind and to present the results of RESA, because he also looked at them, and there we already did deterministic identification. So that means you already have a clue. So Pau is from the Technical University of Munich. In principle, he worked in a joint project of Holger Bocher, Andreas Winter, and myself, which we start in Munich, and when Andreas was in Barcelona. And we all are supervising him. And yeah, he do work on quantum communication and also on deterministic identification. So stage is yours.
Thank you. So yeah, as Kristen said, I want to talk about deterministic identification, which is the topic that I've been following for at least 2 years now. We have some super cool results that I'm gonna try to present. But the main objective of this talk, actually, have I seen that everything today is identification, or most of it is really understand what is identification, why is it cool, why deterministic, and like the deep-rooted concepts, so that everything that follows can be, well, followed, right? So when I started thinking about everything that I wanted to say in this presentation, well, I started drafting an outline. So when I started thinking about everything that I wanted to put on the presentation, I started drafting the outline, and it was huge, and it was like 2 pages long, and I really didn't want to put 2 pages of outline. So I said, okay, I will just do a scroll up with all the results. And if I'm going to do a scroll up, of course, there's only one correct way to do a scroll up, which is, of course, the Star Wars way. And yes, so what we're going to do is first talk about, you're going to see now transmission of messages. When we know transmission of messages, we're going to move to the concepts, rate, capacity, understand them correctly. We'll move to identification. We compare identification and transmission. We'll move to deterministic identification. We will explain these super exponential codes that we have been, well, yeah, discussing for some days now. Then I want to talk about all this stuff about my research that at some point will be interesting to you, I hope. And then I will just run through some other results that I could not fit in this presentation, and that hopefully you will ask, or maybe now or later to discuss them if you're interested in them. So this might be a bit scary. So remember that the fear is the path to the dark side. So let's just push through and start with transmission of messages. So if we have two individuals, in this case, of course, Leia and Han, who want to convey a message, well, they can do so, but we will make things more complicated to them. We will separate them, and we will give them a channel to communicate. Now, Leia will have to choose between a set of messages, and Han will have to guess which message of the set has she sent. So this mathematically, or a bit more mathematically, what we do actually is we take a channel from X to Y, and we use it n times to convey this message. The input space, of course, will be X to the n, and Leia will have his list of messages encoded in points in this Xn. So these are sequences of this input space we encode our messages into. Then Leia will send this message through the channel, and Han, in this case, will get a point in the output. He will decode this point, and hopefully he will get the same message that Leia sent. This is, of course, a very easy picture. This is because it's a noiseless picture, right? We're sending one message, we're getting one output. Sorry, we're sending one input distribution, let's say, we're getting one output distribution. This is not really what happens in when the channel is noisy. When the channel is noisy, what we have is, instead of an output distribution, and we hinted that yesterday already in the poster discussion, we have a probability output distribution between points in the output space. So we can have any point, let's say, in this set, and well, yeah, Han now will have to to create a decision rule here. So create a set of the output space, and if this output sequence is the sequence that he receives is inside the set, then he will choose, okay, the red message was the one that was sent. This, of course, will happen for every message, every possible message in our set, and this will create a mess of output probability distributions in the output space. And of course, as you can see, there are some overlaps in these output probability distributions. So it is possible that when we send one message, we end up in one of these overlaps. So it is possible that if the message, so the output distribution ends up in this output, Han cannot know if the message that was sent was the red one or the green one in this case, right? So what he has to do is, of course, create a decision rule of non-overlapping output probability sets, such, well, as I have tried to draw on the screen, such that there is no way that, so Han can give a certain response to the message that was sent with, of course, some error because of these overlaps that we are overlooking with these decision sets. So now when Leia sends the red message, Han will receive an output distribution, hopefully in this red space here, and he will be able to say, okay, the message red was sent and I am certain of it with this certain probability that I can bound. And this certain probability, the cool thing is that we won't see that asymptotically. So for n going to infinity uses of the channel, this error probability goes to 0. So this is really something that can be controlled. Okay. So this is what our idea, and now what we should do is defining a transmission code more mathematically. We call an NM lambda transmission code a set of sequences on the output, decision sets on the, sequences on the input, decision sets on the output, such that this error probability or this error bound that I have just explained can be fulfilled for each of the messages and decision sets. Yes. Now, the relevant question here is, Leia would ask, how many messages can I send in this setting? What is the maximum of messages that I can send with the minimum uses of the channel? So what is the best that I can do? Of course, if I start packing more and more messages into the input, the output space will start having more and more overlap. So creating a decision rule will be more difficult for Han. Notice now also that this exponential scaling that we can see here. Imagine that we had the identity channel, the identity channel of dimension 2 as a noise rate channel in between. Of course, the number of messages that you can convey is 2 to the n, right? If you have one user of the channel, you can send 0 or 1. If you have two users, you can send 0, 0, 1, 0, 0, 1, 1, 1, and so on and so forth. So you have 2 to the n messages that you can send. If you have an identity channel of size x in this case, you can send x to the n messages. This is really like basic combinatorics, x to the n, which can be written as 2 to the n log x. And actually, if you do that for any channel, this is a natural thing, a base property of transmission, and that you will find a code that scales exponentially, as you can, I don't know, maybe this has served as intuition, hopefully, this exponential thing with some rate, with some number that will depend on the code that we're using, that will depend on the channel. So the difference between rates and capacity. I really think that this is a concept that has to be really understood. Now, we had this exponential scaling for transmission codes, and of course, we can just reverse the equation and define the rate, as you can see here, as the ratio between the number of the logarithm of the number of messages that we can send in this code divided by n. And notice that this is a characteristic, a root characteristic of the code we are using. This is not a property of the channel. This is a property of the particular code that we are using to convey the messages. So, of course, more rate, it's equal to having more messages with less channel users. This is the ratio that is defined above. And of course, given a channel, there are infinite ways to define different codes. We can create many different and clever ways to convey messages. So for any channel, there are infinite codes. Every single code, different code, can have a different rate. The rate is a characteristic of the code. And now the relevant question is, what is the best that I can do with a given channel? So somehow, how can I optimize for a given channel over all codes? What is the number that gives me this characteristic? And this characteristic is the capacity. The capacity is nothing else than the best rate that you can achieve or that is realizable for a given channel. So somehow what you're doing, also in the asymptotic limit of n going to infinity. This is important. So what this is telling you is the capacity is the number that will define this ratio between messages and channel uses for the channel. So for a given channel, the capacity is a property of the channel. The rate is a property of a particular code that we're using. Now, our way to calculate capacities is first constructing a code and trying to see what can we do with this code. This code will, of course, be at least a lower bound on the capacity when we look at the limit of n going to infinity. And yeah, this will, as it is one of the possible options, which will be a lower bound, and we want this code to be as optimum as possible, let's say, so that it is closer and closer to the capacity. And then we are going to look at it from the other way around. We are going to define the characteristics that any possible code has to fulfill to be a transmission or the identification code, and then analyze with this property that all codes have to fulfill, analyze what rates could we achieve. So this will, of course, be an upper bound, and what we want is to approach the upper bound and the lower bound until they reach a common point, hopefully, and that will be the capacity. So, I have this work asymptotically faithful. This is what I already explained. We want that for n going to infinity, the errors go to zero. This is the basic Shannon idea long ago. And a very well-known theorem, it has appeared many times during these days, the Schumacher-Westmolen theorem, that tells you that the capacity, this number here for transmission over a certain channel, is this mutual information between some probability distribution on the input and the channel itself, which can be seen as a stochastic matrix. Now, this is everything I wanted to say about transmission. Identification. In identification, we have, again, a noisy channel. We have our main characters separated. Leia will have to choose between a set of messages. But now Han wants to know only one message. He's interested only to know if the message, in this case, I love you, was sent. Now, Leia will send a message, in this case, I love you, he's lucky, and he will identify this message. Now, notice, in transmission, you had to decode any possible messages that was sent. In identification, we just do a hypothesis test. Is the message that was sent the same as I'm thinking, or is it not? First, I choose a message, then I receive one, and just check if the message I received is the one I want to know or not. Now, this is, of course, on the hand side, this is an easier task, right? And the objective here, if this task is easier, and this has been proven that it has less communication complexity, the question Leia would ask is, can I do better? If this is easier for you, can I send even more messages? And indeed she can. So the first idea that I'm going to present is what happens if I use randomness on the encoder. So what if, instead of encoding my every message in a particular input distribution, in a particular input sequence, what if I create probability distributions on this input space? I create, as you can see, these subsets in the input space, I encode a probability distribution into these subsets, and I encode every message into a probability distribution instead of a particular sequence. Now, why are you making this to me, right? Why would you complicate yourself so much? So the idea here is that we have this theorem, which says that the number of subsets that you can create is actually exponentially larger than the actual number of points that you have. You can create exponentially more subsets of a certain number of input sequences than you can than actual points that are. So if there are m input sequences, you can create something of the order 2 to the m subsets that actually have a small overlap. And this is a very cool property because now if we manage to encode all these messages into the probability distributions over these subsets, then we will be able to transmit exponentially more messages than we could before. Yes, this is exactly what I just said. So the question now is, can I actually identify these probability distributions? Well, yeah, I ran through a bit too much. Now, can I identify these probability distributions? This is what I'm doing here. So the thing is, we had these probability output distributions, we had these input spaces. If now I create these probability distributions on the input space, on the output space, this is so we create also like the union between all these probability distributions somehow. This will look something like that. This picture is maybe not the best one because there are less distributions here than there were before. But you have to remember the theorem before. This would actually be many more, exponentially more subsets of this kind as we had before. But it was kind of impossible to draw, so I just left it here. Now, creating this union, Han will decide on a decision rule and just check if the errors can be controlled. The dots are particular sequences. So you take a subset of particular sequence. For example, I take the blue, brown, red, yellow sequence, and I encode in a probability distribution between them. So my encoded message would be, for example, a uniform distribution between 1/4 of probability blue, 1/4 brown, 1/4 red, 1/4 yellow. Here it's not because I didn't mark the point, but it could be, right? If it's in this subset that we have explained before, in this exponentially more number of subsets. Of course, when you send the message, the thing that is inside the message is not a probability distribution, it's just one message. Just Leia doesn't know which message it is, Han doesn't either. Now we can define and randomized, in this case, identification code, which is just as before, a set of probability distributions on the input and a set of decision rules on the output, such that they fulfill these two error kinds. Why are there two error kinds? The first error kind is exactly the same that we had in transmission. I send one message. Because of the noise of the protocol, this message gets mapped into one of these, well, it gets mapped outside my decision rule, right? So Han mistakenly, so they both think in the same message, and he mistakenly says, oh no, Leia did not send the message I was interested in, though she did. The second kind of error is like the other way around, a false positive. That was a false negative. A false positive, notice the terminology of hypothesis testing, which is Leia and Han think of different messages. Leia sends a different message than the one Han is interested in, but because of these overlaps in the output probability distribution, in the decision rules, Han says, oh yeah, Leia sent the message I'm interested in, though she didn't. This is the second kind of error, and these are the two kinds of error in any hypothesis test, right? Now we have this theorem by Alshvedi and Luke, which says that you can actually identify these probability distributions, let's say, so messages encoded in this probability distribution, indeed with this double exponential nature that we had seen on the lemma before. So as the code sizes are double exponential, we have to define now a capacity that is double logarithmic, right? Because if not, the capacity would be infinity. So if I remove this logarithm here and I have something that scales double logarithmically, I guess, you have here something that scales exponentially with n going to infinity. This is infinity. So I in purpose define a capacity such that I can get a relevant number here, but not 0 or infinity, which would be just trivial. Yeah. We want him to be able to choose any possible sequence, but when the protocol starts, he just looks at one hypersurface in the output. Let me just do a quick comparison between transmission and identification. In transmission, we have to be able to decode any possible message. In identification, just a single hypothesis test on the message I'm interested in. Transmission, we had a single decoding error. In transmission, we have the 2 hypothesis test errors. Transmission, we have deterministic encoding. And actually, if you try to do this randomized encoding in transmission, it wouldn't work. Or it couldn't get better. It could work, but it wouldn't get better in scaling. In identification, we get better with this stochastic encoding. In transmission, we have disjoint output probability sets, or output, not probability, but decision rule subsets. In identification, we have, they are overlapping. And in transmission, we have an exponential scaling. And this is a cool thing. In identification, we have exponentially more messages. So now the thing is, this stochastic encoding, how easy it is to apply. It might be very expensive to do this actually in a lab or in antennas or whatever. So what happens if we try to do deterministic encoding? So the task is still easier. So maybe we can still pack more points here in the input space such that the probability distributions, as the task is easier, can still be identified beyond the scope of transmission, right? Now, why we wanted to do this? Of course, as I said, randomization is expensive, and it is actually, well, deterministic encodings are actually easier to implement, easier to construct. They are more similar to natural models, as people in molecular communication is already thinking, right? How would I apply some randomized encoding in a cell or in one of these nanopods that we've been discussing these days? So, what do we know about this? We know that for discrete memory-led channels, the code sizes can only be exponential. So we get back to the transmission scaling. The rates can be a bit better, but the scaling, let's say the asymptotic performance is the same one, which is a bummer. For some continuous channels, we actually have this super exponential scaling. This is better than transmission. It is worse than identification or randomized identification. This is this n log n scaling. We can actually do this. Maybe I ran through a bit too much through this, but we can actually do this thing. We can actually pack more messages here, and I still identify the outputs. And the definition of a deterministic identification code is very similar to the ones that we had before. We just need a family of points now, not probability distributions, but single points on the input space, a set of decision rules on the output, such that the two condition rules, the two error bounds can be fulfilled. Now, we have seen all these different scalings. We saw that yesterday with Mohammed, that it was also in the poster. So I'm just going to run through it. We have all these different scalings. This is just so that you can see graphically that this is a dramatic improvement. Each one of these steps is actually a dramatic improvement when you look it in for big and big block lengths. So for bigger block lengths, these are actually much and much better. These are, let's say, infinitely better, each one of these steps, when you look it in block length. So for big block lengths. Also, we know that for deterministic identification, we have something here, we have something here, and we have something here. So what is the, let's say, can we create a general theory for deterministic identification? Can we create a thing that or let's say a capacity bound that can comprehend both the results, the super exponential results and the deterministic identification results? This is the kind of questions that we started asking on the beginning of our project. Now, notice that the scaling is super exponential in these deterministic identification codes over Poisson channels and Gaussian channels. So we should define a corresponding capacity. And note that I stress the word define capacity. This is something that we define to make sense of the best possible rate that we can achieve for a given channel. So we define the super exponential capacity now with this n log n, such that the rate in the limit, in the asymptotic limit, will be a number, and not zero, no infinity, but a number. And of course, I just put here the results for the Gaussian and Poisson channel. We're going to go back to this later. Now, this actually compares to the definitions that I have already given in this same presentation for transmission and identification. Notice that I have arbitrarily defined a double exponential capacity. Notice the two dots. I just use the two dots for double exponential so that I don't have to write all this, but only the C. This double exponential thing is something that I have defined such that the codes that are actually double exponential will have a relevant number as the value for the capacity. Of course, if I used this capacity for something that is not double exponential, this capacity will be zero. Of course, if I use the one, so if I have a super exponential scaling and I use this one, it would be zero. If I use the first one, it would be infinity. So I arbitrarily define a capacity, and this is something that is very important. Capacities are something that we define. It's not something in nature. This is a way to find some sense of what is the best thing that we can do. So the best rate that we can achieve, the optimum rate for a channel. It's a channel characteristic that we define. And we are going to define a couple of more capacities you're going to see in some slides. So now, our problem. How does deterministic identification behave in general? Can we explain the difference in scaling for deterministic identification over DMCs, so discrete memory-led channels, and this continued channel result that we have where the capacity is not exponential, but super exponential? Notice the dot. This is what we started to look in the beginning of our project, and this is where our work starts with my beloved supervisors, Christian, Holger, and Andreas, and maybe my muse, Samuel L. Jackson. And well, yeah, let's just start with the results of our project. The first thing is that we built around typicality. Why typicality? Why do we like this? Well, first, what is typicality? So a typical set, in this case, a conditional typical set, is defined as you can see on the screen. And the thing is, if you have an input sequence and you send it through the channel, you have a possible output distributions, right? So which is the subset of, well, first, the typical set is just a subset on the output probability space, not probability, in the output space. This is a subset such that the probability of finding as a sequence in this output set is close to the entropy of the channel when the certain input was or input sequence xn was sent. So why do we like this particular set and not any other set? Well, because it has some very nice properties. First of all, it has almost unit probability. This means that if you send a message xn, the probability of finding an output distribution, not distribution, an output sequence on the typical set is almost 1. It's something good that goes to 1. So this set contains almost all probability, and also the sequences that are on this set are actually kind of equidistributed. So the probability of finding each one of these sequences on the output probabilities, not probability, in the output set, it's actually kind of uniform or almost uniform. And this is a very nice properties for code construction, and this is why we like to use typical sets. Now, of course, this typical set definition is just useful for channels that have a discrete output, right? Because this thing there, this logarithm, well, not the logarithm, but the probability distribution of an output is only well defined if the output is something finite, right? It should be defined in an interval if it was something continuous. So indeed, we will look at everything in full generality. This is the only restriction that we put in our model, in our setup, which is that we will look at channels with arbitrary inputs. It can be whatever, but the output has to be finite so that we can apply these typicality results that we are looking at. Now, a preliminary result. This is something that comes out naturally from this definition of unit probability. We can actually rewrite this to something that actually scales, approaches 1 exponentially. So it's something that is exponentially close to 1. And why do we like this particular expression, this lemma setup instead of that one there when they look so similar? Well, notice that this looks very, very similar as the bound for the first kind of error, which was this thing here. Notice that if our decision rule was this typical set for the input sequence that was sent, this is something that is very similar. And actually, the error probability is something that indeed goes exponentially to zero, let's say, which is actually what we want for our codes, that in the asymptotic limit, the errors go to 0. Now, the question would be, can we do the same for the second kind of error? Can we bound similarly the second kind of error? And this is what we do with what we call the hypothesis testing lemma, which is this thing here that you can see. So we prove that, and this is quite the base result of everything that follows, we prove that if there is enough separation between our output distributions, and when I say separation, I mean total variation distance, so the statistical difference between the output probability distributions. If there is enough distance, then the typical set has this. So the typical set for 2 different messages that convey these 2 different probability distributions has this expression here. Does this look similar than the second kind of error bound? Well, kind of. We could say that this whole thing here could be lambda 2, but notice that this term here is problematic, right? Because this goes to infinity for increasing number of n. So this error here, if we define this as our error, as our lambda 2, this error here would go to infinity, which is something that we cannot allow. So how can we control this? Well, we need to control the second term. The first term is not problematic, actually. As you can see, it's the same as the first one, but we are not happy with the second term. How can we control the second term? We do it in 2 steps. First step, we will restrict ourselves with output probability distributions that have similar entropy, and this will allow us to control this term here, this thing here, which grows actually with n. So the entropy or something that of some probability distributions that scale with n actually grows with n also. So first, we control this term here by imposing that the output probability distributions have similar entropy, and then we define an epsilon as such, as -3 delta square root of n, such that it will somehow win the 2 delta square root of n, and all this thing here will be something that again goes down to 0 for increasing n. Now, the question is, can we construct, well, actually, I already answered it. We can construct the code with these probability distributions and with these typical sets as output distributions. So this actually works if we impose these 2 conditions that will make us control the second term, which is the problematic one in these bounds. Let me re-express this in a better way. We have our useful lemmas there, and the theorem would be if you have enough separation between output probability between output distributions that come from different code words, and this distance, notice that is this epsilon that we have before, and we have now defined such that the second kind of error can be controlled. And then we have a code size of this size here, of this cardinality there, which is n, which is that double exponential thing divided, well, not double exponential, we actually don't know what n is yet, this n divided by some term that actually comes from the first condition here. I'm not gonna get into it so much. If someone is interested, just please ask. And then we can construct code with these errors, which are actually the same that we have in the lemmas, right? We can construct a code using the typical sets as output decision rules, and then we can control the errors. So this is not that in any kind, some kind of converse, this is just the achievability part. We just notice that if you have this separation between distributions, then you can construct a code, and then we're gonna analyze the performance of this code and see where we stand. Maybe this is far away from any meaningful capacity value. Maybe it's good. We're gonna see it. And how are we gonna see it? Well, of course, well, yeah. First, the big words, just from a packing and I'm going to explain what is a packing in a minute. Just from a packing in the output probability set, I can create a deterministic identification code, and not only a deterministic identification code, but a good one, such that the errors go to 0, so on and so forth. Now, what is a packing? The packing problem consists of finding the maximum number of disjoint hypercubes or hyperspheres. The shape actually don't matter. The maximum number of hypercubes, disjoint hypercubes, such that they are with centers on a particular set, such that they are disjoint. Let me just draw this because it will be easier. So if we have, in this case, our output probability set, which is the thing that we want to pack, we want to find the maximum amount of, let's say, hypercubes that I can fit here with them being disjoint, the maximum number of hypercubes that I can fit in this space such that they are disjoint, and the centers, so this one is accepted because the center is inside the output set. So this is the packing problem, and this is what will allow us to calculate this n. So we just need to calculate the size of a packing to know the cardinality of the code, therefore the rate, therefore calculate the lower bound on the capacity. Good. So as I said, the packing centers are now these output probability distributions, and the site of the code, the site of these small squares that we're using is this 1 minus 3 delta square, exponential minus 3 delta square root of n, which is our definition of this epsilon, such that the second kind of error can be controlled. As I said, in the asymptotic limit, this will be lower bound on the capacity because this is just a single code construction that we are using and we are now analyzing. Now, we can simplify this problem even further with what we call spherization. Maybe I will explain where these names come from. I don't know if I will have time. So the thing is, now, first, let us study this negative difference, the negative logarithm of this difference, such that we can study the relevant thing here, which is this exponent here. This is the relevant thing of this distance. So we are motivated to study this, and as it turns out, we can calculate, this is not at all trivial, it takes some work, but we can calculate that this thing here can be actually bounded by this other thing here. And why we like this other thing here better than the first thing there? Well, because notice that this here is an Euclidean distance. And not only an Euclidean distance, but a letter-wise analyzable, let's say, Euclidean distance. So if we try to calculate the packing using this total variation distance thing here, this bound here, we would have to consider first full sequences of output probability distributions, and we will have to pack in that strange output probability space so we would have to pack on the probability simplex. Now, with this change here, we can do a letter-wise analysis, not full sequences, but letter-wise, and also we just need to pack in Euclidean space, actually points in Euclidean space. And this is something very interesting. Why I'm calling this spherization, let me just invent this Bernoulli channel, which has input between 0 and 1, and output, this is, whatever, 0 or 1. I think I made this the other way around, but like in proper mathematical notation. So this inputs a ledger between 0 and 1, let's say x, and outputs with probability x, the outcome 1, and with probability 1 minus x, the output 0. How does this look in a plane? This is just this probability simplex, right? So all the different probability distributions can be seen in this line here on the output space. What are we doing with these square roots? What we are actually doing, and you can check this for this very easy case, we are actually just changing this thing here by the square root, and this thing here by the square root, and this function, it's actually this thing here, which is like the positive part of a sphere of radius 1. Right? So we are moving from a probability simplex to points in this hypersphere, which means that we are moving from a packing in total variation distance in this strange norm one metric that we could define, a packing there in full sequences, to a letter-wise packing in Euclidean space. So packing points in an Euclidean space. This is much, much easier. And also we have many more tools to handle this. Now, the takeaway: to construct a deterministic identification code, we just need an Euclidean packing. And this is fantastic. And then we just need to analyze this Euclidean packing to get a lower bound on the capacity. Of course, if we get, let's say, an optimum Euclidean packing, then we'll find a better bound for the capacity. Now, what can we say about the converse problem that we were discussing at some point? This is just the code construction. I'm going to get to it in 2 slides again. But what can we say about the other problem, the converse problem? This means, what is the minimum condition that any code has to fulfill such that we can create, well, something similar as we just did and calculate the size of that a code with this condition that any code should fulfill has, right? Now, the minimum condition that any code has to fulfill is that the output probability distributions are distinguishable. If the output probability distributions are not distinguishable, you cannot identify anything, right? So this is something that any code has to fulfill, and this is a very basic idea. And as we just did before, it's not trivial actually, but it can be done. We can again find this object here, this Euclidean object that we had. We can transform this bound in something Euclidean. So again, now we will want to define a covering, and you will see why also in a couple of slides. What is a covering? This is the converse problem of the packing. In the packing, we wanted to find the maximum number of squares of a given site that can be fitted in a space. In a covering, instead of packing inside, we want to cover the whole space. We can allow for overlaps between the sets, and we want to find the minimum amount of elements such that I can cover the whole space. You're going to understand in a minute why we're using a covering here and not a packing, let's say. So the second takeaway is, any output distributions from any possible deterministic identification code have to be points in this covering. So analyzing the size of this covering, we can calculate an upper bound of the capacity. Let me put the 2 takeaways together. And let us understand why first a packing, now a covering, so on. So we have seen for the direct part, if I have this condition, I can construct a code. Now, this condition here, this distance here is actually optimized by an optimum packing on the output probability distribution space, actually this Euclidean space, if you want. From the other side, and this is a lower bound on the optimum size of the code. From the other side, we know that any point in any deterministic identification code is part of a covering. So as an optimized covering is the minimum number of squares that you need, this is a lower bound. So an optimized covering is a lower bound on this number, and will be a lower bound on the optimum size of the code. So this is why are we using a covering here, because this is a minimum number of points, and this is a maximum number of points. So an upper bound on the condition that we have is a minimum number, so a lower bound on the condition that we have. So this is why we use this different thing. Now, the way to find the tightest bounds with this method that we can is just analyzing this optimal packing and this optimal covering in Euclidean space. And we find these Euclidean objects, which are actually Euclidean objects, these Minkowski dimensions that you can actually bound the super exponential capacity. What does this mean? First, deterministic identification codes generally scale super exponentially. This is the first takeaway. Any channel has, or any general channel, let's say, behaves super exponentially. We can create a code that behaves like this. And so this is this super exponential scaling is not a particular channels of this Gaussian and Poisson that we saw. Is just it's actually a general thing, a natural thing, a defining characteristic of deterministic identification codes. Second, the bounds that we know for the Gaussian and the Poisson channel can be reproduced or actually improved. For both these channels, these objects are these dimensions here are actually 1, and the upper bound that we knew for the Poisson channel was 3/2, so we improved them or we improve the upper bound by 1 unit, which is good. Third, and most importantly, the bounds are written in terms of this object, this Euclidean object, the Minkowski dimension of the spherization, which is this thing that I just explained here, of the set of output probability distributions. And now you could ask, what the hell is the Minkowski dimension? Let me explain the Minkowski dimension because it can be understood in a very easy way. Let me go back a bit. Imagine a packing of site S. So we want to cover, for example, a line with, in this case, segments of a given site S. If I choose two segments if I choose segments of size 1/2, I can get two different, I can pack this line in two parts, right? If I get segments of size 1/4, I can pack four squares, four segments in this line. Of course, we could scale this, and any packing of a given site S can be, has a size of 1/S, right? This is quite clear. If we do that for a square, so for an object of dimension 2, what we get is so the size of a covering of squares of site 1/2 is 4 elements, right? We can pack 4 small squares of site 1/2 inside the big square of site 1. We can pack 16 squares of site 1/4 into the square root of site 1. So again, we can do the generalization to, in general, for a square, the number of elements of site S that I can pack is 1/S to the power of 2. And you can think about this if you think on a cube, even a tesseract, if you're very imaginative. We can scale this to saying the number of elements in a packing of a given site S is actually 1/S to the power of the dimension, the topological dimension of this set. First, we had 1 for the line. Now we have 2 for the square. If you did that for a cube, you would find a 3. So we could define the topological dimension as this thing here, as the ratio between the logarithm of this number of packing elements that we can find divided by the minus logarithm of the site of the squares that we're using. Of course, if we used a more irregular object, what would happen? Okay, what would happen for this object here, this is, of course, the number of elements that we can pack inside this square is obviously 3/4 of what we could do in this other square there, right? So this is a bit different, but notice that if we make S smaller and smaller, this thing here tends to this other thing there, right? So for small values of S, this thing here is closer and closer, is more similar to this thing here. So maybe a more accurate definition of what the dimension is would be the limit when the site of these squares go to 0 of this ratio between the elements of the covering set and the site of these elements, packing, not covering. And this is actually the definition of a Minkowski dimension. This ratio here. A Minkowski dimension can be defined, as you can see on the screen, by this ratio we had just defined. And actually, the same would happen, the same you would find if you did that for a covering instead of a packing. You get the same value, actually. And what really is the Minkowski dimension, or why do we like it? Because for even more irregular objects, say fractals, the Minkowski dimension does not coincide with the topological dimension. And this is why we need the definition of a Minkowski dimension. Imagine, for example, the typical Koch fractal, which is this kind of snowflakey thing. So this thing here, of course, is a line, of course, has dimension 1, topological dimension 1. But if you do this weird definition of dimension that I just gave you, you get something that is bigger than 1. And actually, it doesn't even need to be a natural number. This thing is an irrational number. So you get something that is different. So the Minkowski dimension is a measure of the complexity of a set beyond the scope of the topological dimension. Of course, for even more irregular objects, so fractals that even more weird than this one, it is possible that the above limit does not converge. So we define the lower and upper Minkowski dimension as the inferior limit and superior limit of the thing that you can see above. And that lower Minkowski dimension is the one that we have in our definition. I ran too much. Oh, maybe I have to do it here like this. So it's the one that we have in our definition of a capacity. And this, I cannot stress enough how weird this result is. we have a capacity bounded in terms of something that measures the complexity of the output probability set. Complexity in the sense of geometrical complexity when you zoom in on the output probability set instead of an entropy measure, mutual information, which is the regular objects that we find for a capacity. So usually capacities are bounded in terms of these probabilistic entropic measures. Here we have something that is purely geometrical, which is, well, to me, beautiful and super puzzling, because this is not some artifact of the proof. I mean, we have both the converse and the co-construction that achieve this. So this is really the defining thing that characterizes a capacity of a deterministic identification, and it's super weird. Okay, now you would say, hey, you're saying all the time deterministic identification codes are super exponential, but we had an example before where the deterministic identification capacity was just exponential, which is the discrete memory-led channel. So what's happening here? What's happening is that this object that bounds the capacity is actually zero. So the capacity, the super exponential capacity is zero, which is exactly what I defined before as a non-useful definition of the capacity. This is just telling you, hey, you cannot achieve with this channel, you cannot achieve the super exponential scaling. So our bounds are, of course, factually correct, but they are not giving actual information on what's happening in this particular channel. So in any channel that would have an output probability distribution set zero, a dimension zero, a Minkowski dimension zero, these bounds that I just gave do not give really meaningful information. So we just did a step back in abstraction, and we just created these other bounds, and these work for any channel. How can we use these bounds? So these are bounds on the maximum size that you can achieve on the set with the same constructions that we had. But now, after you calculate these packing and covering numbers, you would see, like on the paper, you would see the actual scaling, and then you just define, and I stress again, you define the capacity that will give you meaningful information for the channel that you're looking at. This capacity might be exponential, it might be super exponential if the dimension is not zero, it might be anything in between. Actually, we have examples of channels that have capacity n log log n, n log 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 n, n log 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 n. You can create all these different scalings and therefore define all these different capacities such that you find, a meaningful information on the best optimum rate that you can achieve for a given channel, right? So this is actually the more general bound that we have in this work. So another interesting and very weird thing is superactivation. So as it turns out, this lower Minkowski dimension that is the base of our bouncing capacity is actually superadditive. What this means is that you can have a set with Minkowski dimension zero, another set with Minkowski dimension zero. You do the product of these sets, and the Minkowski dimension of the set is bigger than zero. This is superadditivity. And as you can see, you can directly, and this step really is trivial, you can directly move these examples of superadditivity into channels. You can define channels such that the capacity will superactivate. That means you have two channels with capacity zero, super exponential capacity zero. When you put them together, you have a super exponential capacity, which is positive. And this is the first time that this has been seen for IID memoryless non-quantum channels. This was seen in quantum long ago. This was observed in classical cases, but not memoryless, not IID, usually with some memory, varying channels, usually some secrecy capacities. Here we achieve this with no tricks, like nothing on my sleeves. Memoryless, IID, non-quantum, deterministic identification can achieve superactivation. It's, again, weird and interesting. Now, another step about defining capacities. So we are defining the capacity through this inferior limit there, the inferior limit of n going to infinity. What this means is that we are taking the number, the rate that can be realizable for all big enough values of n, right? We're taking the lowest convergence value of the rate. But of course, it would be possible. So the rate function looks probably something like the black line here. Actually, it doesn't even need to be continuous. And we're taking the red line, right? The lowest convergence value. But you could be interested in the best possible performance that could be achieved only by a subset of a given subset of block lengths, such that they achieve the highest convergence value of the rate function. That is the superior limit, and this is how we define an optimistic capacity. So instead of defining it through the limit inferior, we define it through the limit superior. And instead of finding the lower Minkowski dimension, we now find the upper Minkowski dimension. And this can be understood. It's not trivial, but it can be understood intuitively if you remember that the upper Minkowski dimension was the definition of the lim sup of the ratio that we had. The lower Minkowski dimension was the lim inf of that same ratio. So this is just some intuition. The demonstration is actually not so trivial, but well, yeah, here it is. Yeah. Okay. This is actually everything I wanted to say about, well, like really explain. And now I have these different chapters, these different topics that we have investigated, we have seen. They are interesting, but I could not fit in this presentation. So I'm just gonna do a quick review of each one of them. And if you're interested, maybe you can ask me later, like later now or later. Now we can discuss about them. So these capacities do not tell us anything. So a capacity value does not tell us anything about the error of the code. It just tells us that the error will go to zero exponential, so will go to zero for big enough values of the block length. But this does not tell us anything about the error. What if we want, or we are interested in what is the actual error that you commit for a given block length? So we know that for transmissions, when you transmit below capacity, well, the errors vanish exponentially. So does it happen the same in deterministic identification? What is the trade-off between sending more and more, so having a higher rate, sending more and more messages, and committing errors, right? So as it turns out, if you impose that the errors decay exponentially in a deterministic identification code, you lose the super exponential scaling. So if the error goes to zero exponentially, the codes go back to being just exponentially, deterministic identification codes. This tells you how fragile the super exponential result actually is, right? In terms of errors. So under which conditions can we get this exponential scaling? Because super exponential scaling, because we know it is the thing, we just calculated it. So we actually see that we can only recover these super exponential results if we impose the slowest possible scaling of the error, so the slowest possible convergence of the error to zero for increasing n. So again, these super exponential results are actually quite sensitive to the error that you have to commit. Now, we have generalize this to also quantum. It is weird to define something deterministic in quantum, of course, because quantum is intrinsically non-deterministic. So how would you define deterministic identification code over quantum channels? You could say, okay, I'm just going to use pure states, which are the less random between all states, and maybe I can even make them orthogonal so that there is actually the encoding is actually deterministic, right? You can deterministically measure a pure orthogonal state. But this is not quantum, right? This is just a quantum formulation of a classical problem if you use pure orthogonal states. So can we find something really quantum into, that reproduce these results for deterministic identification? If you just impose that you have pure states and you allow for some overlap between these pure states, you actually get back the double exponential scaling. So if you impose pure states, you get back double exponential 2-dodge capacities. So what is the correct, let's say, definition of something that is an analog of deterministic identification in the quantum setting? So we analyze this through a generalization of the hypothesis testing lemma that I presented long ago. And we see that actually we can transmute the same construction that we have in this classical case to a quantum case with this new quantum hypothesis testing lemma. And we prove that for classical quantum channels and fully quantum channels restricted to only using product states as input, then we can find these super exponential scalings. So in fully quantum channels, we find again this super exponential scaling. So this is, let's say, a true analog of deterministic identification in the quantum setting. And finally, just to end, some open questions and things that we're looking at. We would love to close the gap between the lower bound and the upper bound on our capacity. We have this 1/4 and this 1/2. Yesterday, I presented randomly this galaxy codes thing that seemed to bring for a single channel, for the Gaussian channel at least, the 1/4 to 3/8. So hopefully we will be able to finally find a particular value for a closed fixed value for the capacity in this case. This is maybe the biggest problem that we have right now. We would love to find separation between unrestricted and simultaneous capacities in deterministic identification, which is something that I did not explain, sorry. So we would like to know also asymmetric. We actually have some results here already, some asymmetric results for the reliability functions when one error is slow and the other error is fast. We've seen that when they are both fast, you lose super exponential scaling. When they are both slow, you recover super exponential scaling. What happens if only one of them is fast and the other one is slow? And we would actually want to generalize this maybe to non-memory scenarios. It would be a cool step also. So I will appreciate any possible ideas that you could have on ways to apply this or ways to expand these results. And yeah, I think that's it. That's everything from me. Thank you.
Okay, thank you, Pau, for this interesting and cool
weird
talk. Are there questions or comments?
I just wanted to go back to what I asked earlier, maybe about the shape of the decoding areas or subsets, right? Because now you said that it depends on for example, if it's some kind of fractal, like if it's more complex, basically in geometric terms, it's better for the capacity, right?
Yes.
But maybe I repeat myself, but I still don't understand. This is still like the way these receiver side areas look like. It's a property of the channel, right? Because the way the sender selects a code word or designs where each code word lies is not really.
Sure. I mean, of course, as it is a property of the output, the channel is involved. I mean, this Minkowski dimension on the output probability set is, of course, depending on the channel. The thing here is that usually you have, imagine that this is, let's make it in 3 dimensions. Yeah, that would be easier. In 3 dimensions, let this be like the output probability simplex, right? And maybe you could even do the spherization if you wanted. But whatever, let's leave it here. And now what I'm saying is for like usual regular transmission scenarios, you could, for example, never distinguish between things that are like this, that are very close in a very small set here. What I'm saying is that I can actually identify it if when I do this, the zoom in of this thing, this is actually something that has a positive Minkowski dimension. So this is not a property of distances between probability distributions here, actually. It's a property of the complexity of the shape of these probability distributions.
Okay, now this makes sense. Thank you.
It is like super normal that this concept is really like absolutely counterintuitive. It's very, very weird. So it is normal that you would have this kind of questions.
So thank you so much for this amazing tutorial. One thing that I just want to understand if I understood it properly, especially the motivations at the beginning. So what you are trying to do is to have a design that does not consider only one receiver, but considers multiple, correct? And each receiver should be able to identify only one of the possible messages. But the message that is identified by each receiver can be, in general, a different one out of the set.
Yeah.
Is that
you could say
correct?
that.
I
You could say
understood
that, yeah.
correctly?
At least in classical setting, you could say that, yes.
Okay. So practically, following your Star Wars examples, I have Han, but I also have a stormtrooper, and I have somebody else. And obviously, the stormtrooper is not interested about a love message from Layla, but it might be interested about another sentence that she would say about a weapon she's about to use, for example. But Han is not interested in that, but interested. So in that context, then all your optimization is considering all that context.
Notice that actually what you're defining would be a broadcast channel. And here we are just using like point-to-point channel. There's only one sender and one receiver. So in principle, we could have for the same channel, different receivers interested on different messages, but not at the same time simultaneously. That would be a question for Johannes, which he knows a lot about broadcasting in identification.
Because I was just looking at this in the context of an application, right? And I was thinking, well, a possible application is that you have an alarm system where you have different alarm codes, and for each alarm code, you have a different interested receiver that does something. For example, an alarm code is fire, and the sprinkler system gets on, and another alarm code is an electrical, for example, alarm, and the power has to be shut down.
Yep.
So, okay.
This example would be an example of identification, but through a broadcasting channel, because you have one input and several outputs.
So yours is then a strict optimization of only one-to-one channel, where in general your receiver might be interested in any of the message, but just one at a time.
Exactly.
Okay, got it. Thank you so much.
Thank you.
Yeah, but your application is totally right. So if you look at applications, it's really alarm and control systems. Yeah, that's really what you have, because that's what you can do with this.
Thank you.
You're welcome.
So are there more questions or comments? Johannes, of course.
Of course.
So I have a question with regard to the geometry and how special it is to identification. Because, I mean, this Minkowski dimension, you don't see it for Gaussian channels and Poisson channels and so on. So the question is, and you said that somehow like transmission behaves with or has probabilistic quantities, entropic quantities or so, and identification here is like the bounds are purely geometric. Okay, this purely I can get, but would you expect that that when you have some like transmission on fractals or on some other channels than Gaussian would then also be somehow maybe an entropic quantity that somehow contains the Minkowski dimension, or entropic quantity scaled by the Minkowski dimension or something. So is this also actually this geometric approach something applicable to special channels for transmission?
So this is again something very general for any channel. So a result that is very general for any channel. Of course, if you try to create a model for a particular channel, I'm sure you could define any kind of function that you wished regarding the different characteristics of each channel and the actual capacity. And maybe this would be something like these fractal entropies that you were mentioning. But this would not work for other channels. So the point here is so the characteristic on capacity that distinguishes the different channels, as the mutual information does for transmission, is actually something geometrical.
Yes. On the other hand, you can, I mean, if you look at a Gaussian channel and transmission, you also can do everything geometrically in principle. Like,
Sure. I mean, for a particular channel, you can probably define any sort of functions you wish.
My thinking or my possibly suggestion is that for that you can also get basically a more general result that applies to just a wider class of channels if you incorporate also this same geometrical consideration in the transmission results, because for example, for Gaussian channels, of course you don't see it in transmission, but you don't see the Minkowski dimension in identification because it's just one or so. So then
for some channels it's one, for some channels it's not. Right?
I'm saying for Gaussian channels. So for certain channels, I don't think that incorporating the Minkowski dimension would make something less general in any way. It could only make it more general. So that's my suggestion.
Yeah,
that you could get that basically the generality that you gain by incorporating the Minkowski dimension in the identification model might be the same that you gain if you incorporate it in transmission. Only in transmission, it may be hidden in the mutual information. I don't know.
I just don't see how this would, I mean, be relevant in any sense. You have now in transmission like a real function that you know and it's well studied that gives you all the information. Yes, you could complicate it maybe.
But not for all kinds of general probability distributions. Only for a very
but I mean,
ones.
You don't see this behavior in transmission. So why would you incorporate it? That's my point.
Well, maybe I don't see this behavior because I haven't looked at the right channels.
No, but you have in general that this behaves as a mutual information. So any channel behaves with mutual information, right?
What is any channel? Do you have a coding theorem for a general Markov kernels?
Well, I don't know what that is.
That's the most general channel that you probably can define. Just a conditional probability distribution in a general probability space.
But surely you can define the capacity with a mutual information too, right?
Who knows?
Well, there's a theorem which is completely general.
Not completely, but we
okay. Well, we can discuss this later.
One more. How can this theory be generalized if the receiver were interested in a sequence instead of just one of the messages, but a particular sequence of transmitted messages?
Yep, this is what they call, and it's a question that Johannes will be able to answer much better than me. This is K-identification or generalized identification. And Johannes is really looking at it right now, so maybe he can answer better than I can on the specifics about this protocol. And but then, this has been looked at, or is being looked at.
One last.
Yes.
Is your theory still valid and optimal if the receiver were to change the attention to different messages dynamically?
Yeah.
Yes, right?
Yeah.
Okay, that's my understanding.
As long as he doesn't gain any information before deciding the message, like from the receiver before deciding the message that he wants to identify, you would be safe.
I'm thinking related to the state. So the receiver can have a different state in different situations, and so can change the attention. So one time I want to identify message A, and then B, and then C.
This is like a important characteristic of identification. The receiver has to be able to identify any message. At any time, he will only identify one,
yes.
But he has to be able to identify any message.
Okay. And then a generalization of that, can we make it fuzzy? So I want to identify, but I want to be also able to have attention on the other messages, but at the same time, I give more importance to one. So it's not a clear cut, but it's like a fuzzy logic concept.
I guess that you could just, like thinking again on something related to K identification, you could just first identify the set of messages you are interested in, and then try to identify the particular message. So doing like a two-step identification, right?
Okay. Or change from identification and going to transmission.
Sorry?
Change from identification to transmission.
This is something, actually, Johannes is again looking at, he's looked at everything, which is in key identification, you just identify the set of messages you're interested in. And if you identify this message, then you decode it.
Okay. I'm thinking about what I was explaining yesterday about biological systems, right? And so there is an attention mechanism. So now I see why yesterday it was told to me, oh, you should look at identification. So now it's clear after your talk. Okay.
Thank you very much.
Thank you.
So since we are talking about this biologically inspired channels and all, like, does this also stay valid for advection channel, like channel which is influenced by advection or reaction? Like deterministic identification, I understood about
How does that work? Sorry, I'm not familiar with that. So how do those channels work, like mainly?
Okay, like when we are talking about these biological systems, or I was just wondering if I can adapt this for our system when there is this tumor and it is releasing some hormones and it goes through the blood vessels. So basically, either like when we abstract things, like maybe we consider as only a diffusion channel, or sometimes we also consider drift, reactions, or advection, which is posed by this blood flow in the vascular system. So when we're talking about Gaussian channel or Poisson channel, like, do we also have another version of like where we can also apply deterministic identification and advection channel?
Yeah, I guess, I mean, these results here would work for that channel too. So I don't really know how the code construction would look, but the results do work for that channel probably. So if it's the memoryless, I am not sure.
Yeah, that's
there's
the memory channel.
Then I can not be sure of it. So.
Okay.
Yeah, okay. I think one thing was also that this defining of capacities was really important, because in many cases people just take the mutual information even if they don't do transmission. And here we see it's not always good. Perhaps one should think about other concepts. So as soon as you go away from transmission, do something like goal-orientated or semantics, then another metric is perhaps better. I think that's also what was very nice explained in your talk.
I think your talk is my first real tutorial on identification code. I get to this topic, I read the papers, and now I feel pity. Didn't hear your talk earlier. So well explained and really appreciate it. Especially the part, I think at the beginning when you explaining this motivation, the site, it's exponential. So this is, I think I didn't get it when I reading the papers, but yeah, but now it's all makes sense. So thank you very much.
I appreciate it. Yeah, that was really the my main idea in this. As today everything will be about identification. My main idea was, let's try to transmit what really identification is. So I'm happy that it worked, at least for one person.
Okay. Yeah. Then thank you again.